Hey everyone, I'm Jared Kaplan. I'm going to talk briefly about scaling and the road to human level AI, but my guess is for this audience, a lot of these ideas are pretty familiar, so I'll keep it short, and then we're going to do a sort of fireside chat Q&A with Diana. I actually have only been working on AI for about 6 years. Before that, had a long career, the vast majority of my career as a theoretical physicist working in academia. And so how did I get to AI? Well, I want to be brief. Why did I start in physics? It was basically because my mom was a science fiction writer, and I wanted to figure out if we could build a faster than light drive, and physics was the way to do that. I also was very excited about just understanding the universe. How do things work? How do the biggest trends that underlie sort of everything that we see around us, where does that all come from? For example, is the universe deterministic? Do we have free will? I was very, very interested in all of those questions. But fortunately, along the way, during my career as a physicist, I met a lot of very, very interesting, very deep people, including many of the founders of Anthropic that I now work with all of the time. And I was really interested in what they were doing, and I kept track of it. And as I moved from among different subject areas in physics, from Large Hadron Collider physics, particle physics, cosmology, string theory, and on, I got a little bit frustrated, a little bit bored. I didn't feel like we were making progress quickly enough. And a lot of my friends were telling me that AI was becoming a really big deal. And I didn't believe them. I was really skeptical. I thought, well, AI, people have been working on it for 50 years. SVMs aren't that exciting. That was all we knew about back in 2005, 2009 when I was in school. But I got convinced that maybe AI would be an exciting field to work on. And I got very lucky to know the right people, and the rest is history. So I'm going to talk a little bit about how our contemporary AI models work and how scaling is leading them to get better and better. So there are really two fundamental phases to the training of contemporary AI models like Claude, ChatGPT, etc. The first phase is pre-training. And that's where we train AI models to imitate human-written data, human-written text, and understand the correlations underlying that data. And these figures are very, very retro. This is actually from the playground of the original GPT-3 model. And you can see that as a speaker at a journal club, you're probably elephant me to say certain things. The word elephant in that sentence is really, really unlikely. What pre-training does is teach models what words are likely to follow other words in large corpora of text, and now with contemporary models, multimodal data. The second phase of training for contemporary AI models is reinforcement learning. This is another very retro slide. It shows the original interface we used for sort of Claude 0 or Claude -1 back in the ancient days of 2022 when we were collecting feedback data. And what you see here is basically the interface for having a conversation with very, very early versions of Claude and picking which response from Claude was better according to you, according to crowd workers, etc. And using that signal, we optimize, we reinforce the behaviors that are chosen to be good, that are chosen to be helpful, honest, and harmless, and we discourage the behaviors that are bad. So really, all there is to training these models is learning to predict the next word, and then doing reinforcement learning to learn to do useful tasks. And it turns out that there are scaling laws for both of these phases of training. So this is a figure that we made 5 or 6 years ago now, and it shows how as you scale up the pre-training phase of AI, you predictably get better and better performance for our models. And this was something that came about because I was just sort of asking the dumbest possible question. As a physicist, that's what you're trained to do. You sort of look at the big picture and you ask really dumb things. I'd heard it was very popular in the 2010s to say that big data was important. And so I just wanted to know how big should the data be? How important is it? How much does it help? Similarly, a lot of people were noticing that larger AI models performed better. And so we just asked the question, how much better do these models perform? And we got really lucky. We found that there's actually something very, very, very precise and surprising underlying AI training. This really blew us away, that there are these nice trends that are as precise as anything that you see in physics or astronomy. And these gave us a lot of conviction to believe that AI was just going to keep getting smarter and smarter in a very predictable way. Because as you can see in these figures, already back in 2019, we were looking across many, many, many orders of magnitude in compute, in data set size, in neural network size. And so we expected, once you see something is true over many, many, many orders of magnitude, you'd expect it's probably going to continue to be true for a long time further. So this has sort of been one of the fundamental things that I think underlies improvements in AI. The other is actually also something that started to appear quite a long time ago, though it's become really, really impactful in the last couple of years, is that you can see scaling laws in the reinforcement learning phase of AI training. So a researcher about 4 years ago decided to study scaling laws for AlphaGo, basically putting together two very, very high-profile AI successes, GPT-3 and scaling for pre-training, and AlphaGo. This was just a researcher, Andy Jones, working on his own with like his own, I think maybe single GPU back in these sort of ancient days. And so he couldn't study AlphaGo, that was expensive, but he could study a simpler game called Hex. So he made this plot that you see here. Now, ELO scores, I think, weren't as well known back then, but all ELO scores are, of course, is chess ratings. They basically describe how likely it is for one player to beat another in a game of chess. They're used now to benchmark AI models to see sort of how often does a human prefer one AI model to another. But back then, this is just sort of the classic application of ELO scores as chess ratings. And he looked at, as you train different models to play this game of Hex, which is a very simple board game, a bit simpler than Go, how do they do? And he saw these remarkable straight lines. So it's sort of a skill in science to notice very, very simple trends, and this was one. I think it went unnoticed. I think people didn't focus on this sort of kind of scaling behavior in RL soon enough, but eventually it came to pass. So we see that basically you can scale up the compute in both pre-training and RL and get better and better performance. And I think that's sort of the fundamental thing that is driving AI progress. It's not that AI researchers are really smart or they suddenly got smart. It's that we found a very, very simple way of making AI better systematically, and we're turning that crank. So what kinds of capabilities is this unlocking? I tend to think of AI capabilities on two axes. I think the less interesting axis, but it's still very important, is basically the flexibility of AI, the ability of AI to meet us where we are. So if you put, say, AlphaGo on this figure, it would be very, very far below the x-axis, because although AlphaGo was super intelligent, it was better than any Go player at playing Go, it was only able to operate in the universe of a Go board. But we've made steady progress since the advent of large language models, making AI that can deal with many, all of the modalities that people can deal with. We don't have AI models, I think, that have a sense of smell, but that's probably coming. And so as you go up the y-axis here, you get to AI systems that can do more and more relevant things in the world. I think the more interesting axis, though, is sort of the x-axis here, which is how long it would take a person to do the kinds of tasks that AI models can do. And that's something that has been increasing steadily as we increase the capability of AI. This is sort of the time horizon for tasks. And an organization, Meter, studied this very systematically and found yet another scaling trend. They found that if you look at the length of tasks that AI models can do, it's doubling roughly every 7 months. And so what this means is that the increasing intelligence that is being baked into AI by scaling compute for pre-training in RL is leading to predictable, useful tasks that the AI models can do, including longer and longer horizon tasks. And so you can sort of speculate about where this is heading, and in AI 2027, folks did. And this kind of picture suggests that over the next few years, we may reach a point where AI models can do tasks that don't just take us minutes or hours, but days, weeks, months, years, et cetera. Eventually, we imagine AI models or millions of AI models perhaps working together will be able to do the work that whole human organizations can do. They'll be able to do the kind of work that the entire scientific community currently does. One of the nice things about math or theoretical physics is that you can make progress just by thinking. And so you can imagine AI systems working together to make the kind of progress that the theoretical physics community makes in say, 50 years in a matter of days, weeks, et cetera. So what is left, if this sort of picture of scaling can take us very far, what is left? I think that what may be left in order to unlock kind of human-level AI broadly construed is relatively simple. One of the most important ingredients, I think, is relevant organizational knowledge. So we need to train AI models that don't just greet you with a blank slate, but can learn to work within companies, organizations, governments, as though they have the kind of context that someone who's been working there for years has. So I think AI models need to be able to work with knowledge. They also need memory. What is memory if not knowledge? I distinguish it in the sense that as you do a task that takes you a very, very long time, you need to keep track of your progress on that specific task. You need to build relevant memories, and you need to be able to use them. And that's something that we've begun to build into Claude 4, and I think will become increasingly important. A third ingredient that I think that we need to get better at, and we're making progress on, is oversight. The ability of AI models to understand sort of fine-grained nuances, to solve hard, fuzzy tasks. So it's easy right now, and you see an explosion of progress, for us to train AI models that can, say, write code that passes tests, or that answer math questions correctly. Because it's very crisp what's correct and what's incorrect. So it's very easy to apply reinforcement learning to make AI models do better and better at those kinds of tasks. But what we need and are developing are AI models that help us to generate much more nuanced reward signals so that we can leverage reinforcement learning to do things like tell good jokes, write good poems, and have good taste in research. The other ingredients that we need, I think, are simpler. We obviously need to be able to train AI models to do more and more complex tasks. We need to work our way up the y-axis from text models to multimodal models to robotics. And I expect that over the next few years, we'll see increasing continued gains from scale when applied to these different domains. And so how should we sort of prepare for this future, these possibilities? I think there are a few things that I always recommend. One is, I think it's really a good idea to build things that don't quite work yet. This is probably always a good idea. We always want to have ambition. But I think specifically, AI models right now are getting better very, very quickly, and I think that's going to continue. That means that if you build a product that doesn't quite work because Claude 4 is still a little bit too dumb, you can expect that there'll be a Claude 5 coming that will make that product work and deliver a lot of value. So I think that's something that I always recommend, is sort of experiment on the boundaries of what AI can do, because those boundaries are moving rapidly. The next point, I think, is that AI is going to be helpful for integrating AI. I think that one of the main bottlenecks for AI is really just that it's developing so quickly that we haven't had time to integrate it into products, companies, everything else that we do into science. And so I think that in order to sort of speed that process up, I think leveraging AI for AI integration is going to be very valuable. And then finally, I mean, I think this is sort of obvious for this crowd, but I think figuring out where adoption of AI could happen very, very quickly is key. We're seeing an explosion of AI integration for coding, and there are a lot of reasons why software engineering is a great place for AI, but I think the big question is sort of what's next? What beyond software engineering can grow that quickly? I don't know the answer, of course, but hopefully you guys will figure it out. So that's it for the talk. I want to invite Diana on stage for a chat.
YC's next batch is now taking applications. Got a startup in you? Apply at ycombinator.com/apply. It's never too early, and filling out the app will level up your idea. Okay, back to the video.
That was an awesome talk about all the scaling laws. And recently, Anthropic just launched Claude 4, which is just available. Curious, how does it change what is possible as all these model releases keep compounding for the next 12 months?
I think that we'll be in trouble if it's 12 months before an even better model comes out. But I guess a few things with Claude 4. I think that with Claude 3.7 Sonnet, it was already really exciting to use 3.7 for coding. But I think something that everyone noticed was that 3.7 was a little bit too eager. Sometimes it just really wanted to make your tests pass, and it would do things that you don't really want. There are a lot of like try excepts, things like that. So with Claude 4, I think that we've been able to improve the model's ability to act as an agent specifically for coding, but in a lot of other ways, for search, for all kinds of other applications. But also improve its supervision, the sort of oversight that I mentioned in my talk, so that it follows your directions and hopefully improves in code quality. I think the other thing that we've worked on is improving its ability to save and store memories. And we hope to see people leveraging that because Claude 4 can blow through its context window with a very complex task, but can also store memories as files or records, retrieve them in order to sort of keep doing work across many, many, many context windows. But I guess finally, I think that the picture that scaling laws paint is one of incremental progress. And so I think that what you'll see with Claude is that steadily it gets better in lots of different ways with each release. But I think that scaling really suggests a kind of smooth curve towards what I expect is kind of human-level AI or AGI.
Is there some special feature that a lot of the audience here are gonna get excited? Some beta that you can, some alpha leak you can give everyone on what you think people are gonna fall in love with the new APIs?
I think the thing that I'm most excited about is sort of memory unlocking longer and longer horizon tasks. I think that like as time goes on, we're gonna see Claude as a collaborator that can sort of take on larger and larger chunks of work.
This is to your point of all these future models being able to take bigger and bigger tasks right now. At this point, they're able to do tasks in the hours?
Yeah, I think so. I think it's a very imprecise measure, but I think that right now, if you look at sort of software engineering tasks, I think Meter literally benchmarked how long it would take people to do various tasks, and yeah, I think it's a time scale of hours. I think just like broadly as people work with AI, I think that the people who are skeptics of AI will say correctly that AI makes lots of stupid mistakes. It can do things that are absolutely brilliant and surprise you, but it can also make basic errors. I think one of the sort of basic features of AI that's different about the shape of AI intelligence compared to human intelligence is that there are a lot of things that I can't do, but I can at least judge whether they were done correctly. I think for AI, the judgment versus the generative capability is much closer, which means that I think that a major role people can play in interacting with AI is kind of as managers to sort of sanity check the work.
Which is fascinating because one of the things we observed through the batches in YC last year, a lot of companies, when they were out and selling products, they were selling it more still as a copilot where you would have a copilot, let's say for customer support, where you still need the last human approval before they would send the reply for a customer. But one thing that has changed just in the spring batch, I think a lot of the AI models are very capable to do tasks end to end, to your point, that, which is remarkable. Founders are selling now directly replacements of full workflows. How have you seen this translate to what you hope the audience here will build?
I think there are a lot of possibilities. Basically, it's a question of what level of success or performance is acceptable. There are some tasks where getting it sort of 70% right is good enough, and others where you need 99.9% to deploy. I think that, honestly, I think it's probably a lot more fun to build for use cases where 70 or 80% is good enough, because then you can really get to the frontier of what AI is capable of. But I think that we're sort of pushing up the reliability as well. So I think that we will see more and more of these tasks. I think that right now, human AI collaboration is going to be the sort of most interesting place, because I think that for the most advanced tasks, you're really going to need humans in the loop. But I do think in the longer term, there'll be more and more tasks that can be fully automated.
Can you say more about what you think the world's going to look like with this human to AI loop collaboration? Because there's the essay from Dario with Machines of Loving Grace that he paints this picture that's very optimistic. And what are the details of how we get there with this loop?
I think that we already see some of that happening. So at least when I talk to folks who work in, say, biomedical research, with the right sort of orchestration, I think it's possible to take frontier AI models now and produce interesting, valuable insights for, say, drug discovery. So I think that's already starting to happen. I guess an aspect of it that I think about is that, like, there's sort of intelligence that requires a lot of depth, and intelligence that requires a lot of breadth. So for example, in math, you can sort of work on trying to prove one theorem for a decade, like Riemann hypothesis or Fermat's last theorem. I think that's sort of solving one very specific, very hard problem. I think there's a lot of areas of science, probably more so in biology, maybe interestingly in psychology or history, where putting together a very, very large number of pieces of information across many, many different areas is kind of where it's at. And I think that AI models during the pre-training phase kind of imbibe all of human civilization's knowledge. And so I suspect that there's a lot of fruit to be picked in using that sort of feature of AI that it knows much, much more than any one human expert. And therefore, you can kind of elicit insights, putting together many different areas of expertise, say across biology, for research. So I think that we're making a lot of progress on making AI better at deeper tasks, like hard coding problems, hard math problems. But I suspect that there's a particular overhang in areas where putting together knowledge that maybe no one human expert would have, where that kind of intelligence is very useful. So I think that's something that I'd expect to see more of, is sort of leveraging AI's sort of breadth of knowledge. In terms of how exactly it will roll out, I really don't know. It's really, really hard to predict the future. Scaling laws give you one way of predicting the future, which says this trend is going to continue. I think a lot of trends that we see over the long haul, I expect will continue. I mean, the economy, the GDP, these kinds of trends are really reliable indicators of the future. But I think in terms of in detail how will things be implemented, I think it's really, really hard to say.
Are there specific areas that you think a lot more builders could go into and build with these new models? I mean, there's a lot that has been done, let's say, for coding tasks. But what are some tasks that have a lot more greenfield that are just getting unlocked right now with the current models?
I come from a research background rather than business, so I don't know that I have anything very deep to say. But I think that, like, in general, any place where it requires a lot of skill, and it's a task that mostly involves sort of sitting in front of a computer, interacting with data. I think finance, people who use Excel spreadsheets a lot. I think I expect law, although maybe law is more regulated, requires more expertise as a stamp of approval. But I think all of these areas are probably greenfield. I think another that I sort of mentioned is how do we integrate AI into existing businesses? I think that like when electricity came along, there was some long adoption cycle, and the very first, simplest ways of, say, using electricity weren't necessarily the best. You wanted to not just replace a steam engine with an electric motor, you wanted to sort of remake the way that factories work. And I think that probably leveraging AI to integrate AI into parts of the economy as quickly as possible, I expect there's just a lot of leverage there.
Now, other question is, you have extensive training as a physicist, and you're one of the first to really observe this trend with scaling laws. And it probably comes from being a physicist and seeing all these exponentials that happen naturally in nature. How has that training come about with being able to perform like the best research in the world with AI?
I think the thing that was useful from a physics point of view is looking for the biggest picture, most macro trends, and then trying to make them as precise as possible. So I remember meeting like kind of brilliant AI researchers who would say things like, learning is converging exponentially. And I would just ask really dumb questions like, are you sure it's an exponential? Could it just be a power law? Is it quadratic? Like exactly how is this thing converging? And it's a really dumb kind of simple question to ask, but basically I think there was a lot of fruit to be picked and probably still is in trying to make the big trends that you see as precise as possible, because that, I don't know, gives you a lot of tools. It allows you to ask like, what does it really mean to move the needle? I think with scaling laws, the holy grail is finding a better slope to the scaling law, because that means that as you put in more compute, you're going to get a bigger and bigger advantage over other AI developers. But until you've sort of made precise what the trend is that you see, you sort of don't know exactly what it means to beat it and how much you can beat it by, and how to know systematically whether you're achieving that end. So I think those were kind of the tools that I think I used. It wasn't necessarily like literally applying, say, quantum field theory to AI. I think that's a little bit too specific.
Well, are there specific physics heuristics like renormalization, symmetry that came in very handy to really keep observing this trend or measuring it?
Something that you'll observe if you look at AI models is that they're big. Neural networks are big. They have billions, now trillions of parameters. That means that they're made out of big matrices, and basically studying approximations where you take the limit that neural networks are very big, and specifically that the matrices that compose neural networks are big, that's actually been kind of useful. And that's something that actually was a well-known approximation in physics and in math. That's something that's been applied. But I think generally, it's really asking very naive, dumb questions that gets you very far. I think AI is really, in a certain sense, only like maybe 10, 15 years old in terms of the current incarnation of how we're training AI models. That means that it's an incredibly new field. A lot of the most basic questions haven't been answered, like questions of interpretability, how AI models really work. And so I think there's really a lot to learn at that level rather than applying very, very fancy techniques.
Are there specific tools in physics that you apply for interpretability?
I would say that interpretability is a lot more like biology. It's a lot more like neuroscience. So I think those are kind of the tools. There is some more mathematics there, but I think it's more like trying to understand the features of the brain. The benefit that you get with AI over neuroscience is that you can really measure everything in AI. You can't measure the activity of every neuron, every synapse in a brain, but you can do that in AI. So there's much more data for reverse engineering how AI models work.
Now, one aspect about scaling laws, they've held for over 5 orders of magnitude, which is wild. This is a bit of a contrarian question, but what empirical sign would convince you that the curve are changing? That maybe we're getting off the curve?
I think it's a really hard question, right? Because I mostly use scaling laws to diagnose whether AI training is broken or not. So I think that once you see something and you find it's a very compelling trend, it becomes very, very interesting to examine where it's failing. But I think that my first inclination is to think if scaling laws are failing, it's because we've screwed up AI training in some way. Maybe we got the architecture of the neural network wrong, or there's some bottleneck in training that we don't see, or there's some problem with precision in the algorithms that we're using. So I think it would take a lot to convince me, at least, that scaling was really no longer working at the level of the sort of these empirical laws, because so many times in my experience over the last 5 years, when it seemed like scaling was broken, it was because we were doing it wrong.
Interesting. So I guess going into something very specific that goes hand in hand is a lot of the compute power required to keep going on this curve. What happens as compute becomes more scarce? How far down do you go into the precision ladder? Like, do you explore things like FP4? Do you explore things like ternary representations? What are your thoughts around that?
Yeah, I mean, I think that right now, AI is really inefficient because there's a lot of value in AI. So there's a lot of value in unlocking the most capable frontier model. And so companies like Anthropic and others are moving as quickly as we can to both make AI training more efficient and AI inference more efficient, as well as unlocking frontier capabilities. But a lot of the focus really is on unlocking the frontier. I think that over time, as AI becomes more and more widespread, I think that we're going to really drive down the cost of inference and training dramatically from where we are right now. I mean, right now we're seeing sort of 3x to 10x gains algorithmically and in sort of scaling up compute and in inference efficiency per year. I guess like the joke is that we're going to get computers back into binary. So I think that we will see much, much lower precision as one of the many avenues to make inference more efficient over time. But sort of we're very, very, very out of equilibrium with AI development right now. AI is improving very rapidly. Things are changing very rapidly. We haven't fully realized the potential of current models, but we're unlocking more and more capabilities. So I think that what the equilibrium situation looks like, where AI isn't changing that quickly, I think is one where AI is extremely inexpensive, but it's sort of hard to know if we're even going to get there. Like AI may just keep getting better so quickly that sort of improvements in intelligence unlock so much more, and so we may continue to focus on that rather than, say, getting precision down to FP2.
Which is very much the Jevons paradox. As intelligence becomes better and better, people are going to want it more. Not that is driving the cost down, which is this irony, right?
Yeah, absolutely. I mean, I think that, that's certainly something that we've seen, that there are certain points where AI becomes accessible enough. That said, I think as AI systems become more and more capable and can do more and more of the work that we do, it's going to be worth it to pay for frontier capabilities. So I think it's a question that I've always had and continue to have, is kind of like, is all of the value at the frontier, or is there a lot of value with kind of cheaper systems that aren't quite as capable? And I think this sort of time horizon picture is maybe one way of thinking about this. I think that you can do a lot of very simple bite-sized tasks, but I think it's just much more convenient to be able to use an AI model that can do a very complex task end-to-end, rather than requiring us as humans to sort of orchestrate a much dumber model to break the task down into very, very small slices and put them together. So I do kind of expect that a lot of the value is going to come from the most capable models, but I might be wrong. It might depend, and it might really depend on the capabilities of AI integrators to sort of leverage AI really efficiently.
What advice would you give this audience, which everyone is early in the career with lots of potential, in terms of how to stay relevant in the future where all these models are going to become so awesome? What should everyone be really good at and study and to still do really good work?
I think, as I mentioned, there's a lot of value in understanding how these models work and being able to really efficiently leverage them and integrate them. And I think there's a lot of value in kind of like building at the frontier. I don't know, we could turn it over to the audience for questions.
Let's turn it out to the audience for some questions.
I had a quick question on the scaling laws. You show that a lot of the scaling laws are like linear, that like the more we have exponential compute going up, but then like we have linear progress in the scaling laws. But then on your last slide, you show that you expect then suddenly like an exponential growth in like how much time we save. I want to ask you, like, why do you think that suddenly on this chart we're exponential and not linear anymore? Thank you.
Yeah, this is a really good question, and I don't know. I mean, the meter finding was kind of an empirical finding. The way that I tend to think about this is that in order to do more and more complex longer horizon tasks, what you really need is some ability to self-correct. You need to be able to sort of identify that you make a plan and then you start executing on the plan. But everyone knows that our plans are kind of worthless, and we encounter reality, we get things wrong. And so I think that a lot of what determines the horizon length of what models can accomplish is their ability to notice that they're doing something wrong and correct it. And I think that's not sort of like a lot of bits of information. It doesn't necessarily require a huge change in intelligence to sort of notice one or two more times that you've made a mistake and how to correct that mistake. But if you sort of fix your mistake, maybe you sort of, on the order, sort of double the horizon length of the task. Because like, instead of getting stuck here, you get stuck twice as far out. So I think that's sort of the picture that I have, that like you can kind of unlock longer and longer horizons with relatively modest improvements in your kind of ability to understand the task and self-correct. But that just kind of like, those are just words. I think the empirical trend is maybe the most interesting thing, and maybe we can build more detailed models for why that trend is true, but it's sort of your guess is as good as mine.
Yeah, so I also have a question over here. So it's an honor. So basically, in terms of increasing the time horizon, I feel like, so my mental model of neural networks is very simple. If you want them to do something, you train on such data. So if you want them to, if you want to increase the time horizon, you have to slowly get, for example, verification signals. Now, I think one way to do this is via product. So like, for example, Claude's agent, and then you use the verification signal to incrementally improve the model. Now, my question is basically, this works really nicely for example, coding, where you have a product that is sufficiently good such that you can deploy it and then get the verification signal. But what about other domains? Like in other domains, are we just scaling data labelers to AGI, or is there a better approach?
Yeah, it's a good question. I mean, so when sort of skeptics ask me sort of why do I think we will be able to sort of scale and get something like broadly human level AI, it's basically because of what you said. There is some sort of very kind of operationally intensive path where you just sort of build more and more different tasks for AI models to do that are more and more complex, more and more long horizon, and you just sort of turn the crank and train with RL on those more complicated tasks. So I sort of feel like that's the worst case for AI progress. And I mean, given the level of investment in AI, and I think the sort of level of value that I think is being created with AI, I think people will do that if necessary. That said, I think there are a lot of ways of sort of making it simpler. The best is to have an AI model that is trained to oversee and supervise what Claude, like you have Claude, say, which you're training to be Claude. When you have another AI model that's sort of providing supervision and is not just saying, did you do this incredibly complicated task correctly? Like, did you become a faculty member and get tenure? Will that take 6 or 7 years? Is that like an end-to-end task where at the end you sort of either get tenure or not over 7 years? That's ridiculous. That's very inefficient. But instead can provide more detailed supervision that says, you're doing this well, you're doing this poorly. I think that sort of as we're able to use AI more and more in that kind of way, we'll probably be able to make training for very long horizon tasks more efficient. And I think we're already doing this to some extent.
We'll do one last question.
Yeah, I wanted to build on top of that. When you're basically developing like these tasks and then training them with RL, would you like try creating these tasks like using large language models, like the tasks you use for RL, or are you still using humans?
Great question. So I would say a mix. I mean, obviously, we're building the tasks as much as possible using AI to sort of like, say, generate tasks with code. We do like also ask humans to create tasks. So it's basically some mixture of those things. I think that as AI gets better and better, hopefully we're able to leverage AI more and more. But of course, the frontier of the difficulty of these tasks also increases. So I think humans are still going to be involved.
Okay, thank you.
All right, let's give it a round of applause to Jared. Thank you so much.
Thanks.